Local Area Networks. This is Module 8, and today we're going to go over what local area networks are. We're going to drill into Ethernet standards, look at the protocol that Ethernet uses, that's CSMA CD, or Carrier Sense Multiple Access and Collision Detection. We're going to go over Ethernet communication methods, and we're going to drill down a little bit further into that MAC address and try and get an understanding of why it's unique and what makes up the different parts of a MAC address. So, Ethernet standards. So in 1982, Ethernet was actually standardized, and what that meant is that the IEEE, and here let me get my handy dandy marker out. The IEEE, IEEE set an engineering standard that would define what Ethernet is, and that is IEEE 802.3. Now, Ethernet was originally invented by Xerox, and at the time there was a lot of other layer 2 protocols that were going on at the time. A lot of local area network communications protocols that were in use. Token Ring was the big one at the time. You had Token Ring. You had Novell, IPX, SPX. There was Banyan Vines. There was Mainframe was using SNA. That wasn't necessarily a LAN, but there were SNA networks that were out and in use at the time. But when Xerox came out with Ethernet, it was in the mid 70s, 75 possibly, somewhere around there. The max speed on Ethernet was 3 megabits per second, and a lot of people didn't really like Ethernet because it was very gabby. Well, Ethernet, it's a broadcast, it's a layer 2 broadcast protocol. The whole way Ethernet functions is by all the machines just kind of getting on the network and just kind of saying what they have to say. It's a broadcast network. Remember how we brought up the example of standing in the middle of a room and just shouting out someone's name? Well, that's essentially what Ethernet was. And most people at the time were not too sure about whether that was a good thing or a bad thing. You end up with a very chatty network, and you end up with some broadcast storms. You had all kinds of crazy stuff going on. And especially going back to what I was saying before with Token Ring, is that Token Ring was nice and quiet, and you had computers that were sitting off this ring, and it ran at 4 megabits a second. And so that was, well, this Ethernet thing is slower than Token Ring. Why do I need it? I got a nice fast 4 megabit Token Ring. And the difference with Token Ring is that if a computer got on the network, they would have a token, and when they had that token, they were allowed to get on the network and send their data through the network. When it reached the destination computer, they would get the token and they would receive the information that was destined for them. Then they would put their information in the payload and send their token and their information back across around the ring. And it was that methodology, this token passing type technology is what was going on. And Ethernet was very, very different at the time. And so there was a lot of different types of cable that also started to come out that Ethernet was able to use at the time. And in 1982, when Ethernet was standardized, we had three main types of physical cable that was in use. We had 10-base-5, which was called thicknet, which was a coax cable. We had 10-base-2 that was also known as thinnet, which is again another type of coax, a smaller coax. And then we had 10-base-T, which is a twisted pair, which is very similar to what we have today with our Cat5 and Cat6 cables. So and I wanted to break some of this down just as a small history lesson, just so you can kind of get an idea of where we came from. But with thicknet, what thicknet did was very interesting. You had this very thick cable that would run through the ceiling of, say, an office or a company, and then they would tap into this thick cable and run a smaller cable down the wall to the computer. Well, when they would tap into it, they used these things called vampire taps. And honestly, that's exactly what they were called. They were called vampire taps because they had these little teeth that would pierce the shielding on the thicknet cable to make contact with the wire inside, and then this transceiver here would convert that signal to be run over the thinner cable to an AUI. This is an AUI connector. Some people may remember this, and then finally plug into your computer. Well, you had a lot of these little guys, these little taps that would go in along the way throughout the office to cable up your network. Well, the next one was, this was okay, but you end up with a lot of issues with these vampire taps. So then they went to a model where you had we're using thinnet. Plus, the thing is, thicknet, being a thick cable, was very expensive cable. It was a lot of copper and it was very expensive. So they went with a thinner cable. It was much easier to use. It was easier to run through the ceiling. But then what you had is, instead of one long bus, you'd run through the ceiling, then you'd run this thinner cable down through the wall, back up the wall, then across to the next room, down the wall, back up the wall, to the next room, then down the wall, back up the wall, to the next room, and so on. And then what would happen is at the bottom of the wall where you'd create your jack, you would pull the cable out of the wall and you would put this BNC connector on it, this little T connector, just like we see here in this picture here. And this BNC connector would then connect to your network card that would go in your computer. See, and then they would each connect to the computer. And that was fine and all, but there was still some more problems where if you had a computer, you needed to work on a computer, and you disconnected that computer from the network. Well, that would end up a lot of times causing all kinds of impedance problems, and the characteristics of the cable would change, and a lot of times desktop technicians would bring down the entire network just to work on one computer. So that really wasn't a good thing either. So we finally ended up going with the twisted pair and what would eventually become star topologies. So as things evolved, in 1982 we saw that Ethernet was standardized by IEEE, and then the need for speed started to occur. In 95 we saw 100 megabits become standardized, and that was just, I remember everybody was just, yoo-hoo, 100 meg. And then we started to see some little flexibility where you could actually do 10 100, where you could be either 10 meg or 100 meg. And what was great about this is, especially for companies who had a large investment in 10 meg Ethernet, now that 100 meg was out, they could utilize and keep that same investment by just upgrading their network cards and keep the same cable and a lot of times some of the same infrastructure devices in order to upgrade to 100 meg. It would all depend. And then remember what I was talking about, my example with Token Ring. Well, Token Ring was 4 megabits a second. But then when Ethernet came out at 10 meg, well, that dwarfed Ethernet. And so a lot of people started to leave Token Ring to go to Ethernet, but not everybody. Because just not too long after that, Token Ring bumped up their speed to 16 megabits a second. Well, that was pretty cool, but then when 100 meg came out, it totally left Token Ring in the dust. And then, of course, it's been just about the de facto standard ever since. In 2000, we saw that gigabit became standardized, and then we started seeing more wider use of it as uplinks and for backup networks, because you started seeing a lot of saturation of your links, and it was mainly things like uplinks and backup segments where you had a lot of servers, and boy, man, my writing is terrible, where you had a lot of large files being transferred. So a lot of companies started opting to go with 1,000 meg for their uplinks and their backbones. Well, today what we're seeing, let's continue on with this, but we see in 2002, 10 gig was standardized, and then eventually 2007, 100 gig was standardized. And you're probably thinking, oh my God, 100 gig? I don't even have 10 gig in my environment. Well, That's true, and 100 gig is still very not so very not so widely used. But a lot of companies today, and it's 2010, almost 2011, are starting to roll out 10 gigabit. The price of 10 gigabit is starting to come down to where it's feasible. We've got a lot of video and we've got a lot of voice that is really chewing up our bandwidth, and we're really needing, again, uplinks and backups are really needing the bandwidth, and so we're seeing a lot more companies go to 10 gig. Some go to Ether channel. We'll get into that. That's a more advanced topic. What Ether channel is? It's more of a bonding of multiple gigabit links together. But 10 gig, whoo, man, that is smoking. And 100 gig, oh my God, that's mainly some of your DoD folks may be using that, and very experimental stuff going on with that. So let's go over some of our packet sizes and exactly what all these big numbers mean. So a byte, just to kind of give an example, 1 byte is actually equivalent to a character. And what I mean by a character, I mean a letter or a number on your keyboard. To create that one letter of data, a single letter's worth of data takes 1 byte of information to go across your network for 1 letter. So 1 byte. Now, one thing I want to point out, if you go back here, notice these are all in megabits per second, little b. Bytes traditionally are shown with a capital B. So 1 byte, just to make sure it's very significant. So if 1 letter or 1 character is a byte, a kilobyte is, well, it's 1,024 bytes. And the nice thing as we move up, a megabyte, well, that's 1,024 kilobytes. And the same, it keeps going on. We have a gigabyte is 1,024 megabytes. And a terabyte, of course, is the same. It's 1,024 also. And you're like, wow, why couldn't we have just rounded that off and just made it 1,000? Well, there actually is a reason to it, but for now we'll just consider that 1,000. Well, let's go back down to our little old bit. Well, this is nice and even here, isn't it? Going from byte to kilobyte to megabyte, it's just 1,024, 1,024, 1,024. It's very easy to remember. But a byte, how many bits do you think are in a byte? Well, if you guessed 8, you're correct. 8 bits make up a byte. Now that's kind of the oddball in the whole equation, but that's okay. 8 bits making up a byte. It actually there is some history there too. If you ever get a chance to Google the baud code, B-A-U. Let me write this up here. B-A-U-D-O-T, baud. Or it was also short for baud. And this used to be a measurement of communication when you would have it. Remember, some of you may remember when we had 75 baud modem. Well, the baud code was actually equivalent to a baud was equivalent to a letter. Sorry, I was going to say a word, but it's actually a character. So 1 baud was 1 character. Well, you can see in a 75 baud modem, that's 75 characters. Somebody who's a really fast typist, I know some secretaries out there that can smoke on a keyboard. They can type faster than 75 baud, and that ended up being a problem, a real problem, because you had humans could outrun the network, outrun a modem, and then you start having all kinds of errors and stuff. But a lot of these technologies kind of come together where you have a single character is 8 bits in length or 1 byte. Now, going back, I wanted to make sure that you understood, though, that when we start talking about our network speeds, we traditionally refer to our network speeds in bits per second. So if I have my home connection, my DSL that I get from my cable provider, they give me a whopping 3 megabits per second. Woohoo! 3 megabits per second. Well, if that was 3 megabytes per second, that's a big thing. If I had my buddy come over to me and said, "Oh, Joe, oh my God, you won't believe it, I got a new provider, it's Verizon Fios, and they're going to give me 3 megabytes a second." And I have to look at him kind of sideways, and he's like, "What? 3 megabytes per second? Well, multiply that times 8 will give you your megabits per second. So if it was 3 megabytes, that would be 15 megabits per second. So there's a big difference between bits and bytes. Now, where are you going to see bytes, especially in measurement? Most of the time you're going to see bytes when you're referring to storage. Like your disk space is going to be measured in bytes. RAM, a lot of times on a computer, is measured in bytes. With networks, though, we traditionally measure things in bits per second. You just want to keep an eye on the B. Make sure it's a little b, not a big B, because that'll be a big difference. So here we have our OSI model, friendly OSI model, and I hope all of you guys have memorized this by now. Here are all the different steps and what each of the different layers do. But what I want to really focus in on today is I want to talk about the physical and data link layer as it pertains to Ethernet. So in the physical layer, we have standards that are for our physical layer. The twisted pair cable, for example, we have category 5, category 5E, 6E. These are standards for twisted pair. For fiber optic cable, we also have multi-mode, single mode. There's a lot more than that, but those are just some examples of some physical standards for cabling that we currently use today with Ethernet. In the data link layer, however, the data link layer is actually split into 2 layers, and you're probably like, "Oh my God, 2 more layers? I just memorized 7 layers. Now I got 2 more layers?" Well, these 2 layers, it's not that bad, and they'll make some sense. But if you remember back when we were talking about the MAC address, well, there's actually 2 layers. There's the media access control layer, or the MAC layer, and the logical link control layer, or the LLC layer. Now, which one of these layers do you think the MAC address resides in? Well, if you said the MAC layer, you are right. I mean, it makes total sense. The MAC layer is a representation. The MAC address was a representation of our physical hardware, right? That's the address of the hardware, the physical NIC in our network interface card in our computer. What the logical link control layer does is it provides a logical connection from that hardware up to our network. Remember a while back when we were talking about IP addresses? IP addresses were a logical address. Remember, especially when we were talking about MAC addresses and IP addresses. The IP address was the logical address, wasn't it? And the MAC address was the hardware address. Well, the LLC, the logical link control layer, actually provides that link between the hardware and the logical IP address, the logical address. So that's what the purpose of those two different sublayers of the data link layer do. Carrier sends multiple access control with collision detection. Oh my God. That's a pretty big mouthful, isn't it? Well, the protocol that Ethernet uses is called CSMA CD, or Carrier Sense Multiple Access with Collision Detection. So I think the best way to kind of break this down is to just kind of like take it real slow. I know it seems pretty daunting to look at the word, but if we break it down, I think it'll make a little bit more sense. So with Carrier Sense Multiple Access, just the CSMA part, what we have is carrier. And what carrier means is the carrier is the signal that actually carries the data. So a carrier, you can think of a carrier signal as if you have a river. Imagine a river and you have an inner tube and you're going to go tubing down the river. Well, if you were to you get in that tube and you're floating in the river and you let go of the bank, you're going to start floating down that river, and that current of the river is going to take you down. The current is going to take you down the river. Well, a carrier wave or carrier signal is similar to that in that there's this signal that's traveling down your network, and it carries your data along with it. So a carrier signal is the signal that carries the data. Carrier sense, or the sense part of this of carrier sense multiple access of CSMA, is the ability to sense that signal exists. A carrier sense is the ability for your computers to sense that the carrier is present on the network. Multiple access, well, it's a local area network. There are multiple computers and multiple devices all accessing that data that's riding the signal that's traveling over your network. So CSMA is just the protocol that allows your computers to sense and get on that signal that's going over the network. Now, collision detection. What collision detection is, and my definition I have down here, is the ability to detect when a collision occurs and how to correct for it. So computers, what they do is when you have a large network, and I'm talking about a really large network, and you have a bunch of computers on here, and they're all chatting at the same time. Well, eventually, what's going to happen is as they're each putting these packets onto the network, eventually, two of those packets are going to collide. They're going to run into each other. They're going to have a collision. Well, what collision detection does is on every computer on the network, they all have the ability to sense when a collision has occurred. When a collision has occurred, what happens is all the computers will sense that the collision has occurred, and they'll all stop sending, and then at the same time, a random timer sets off inside the network card. And since this timer is random, every computer on the network then will have a random number, and whoever has the highest number will then be allowed to send their data on the signal. Now, they're not talking about this. Basically, it's just a random number, and if I roll a number, and if I get a 1, I'm going to go. So whoever gets the 1 gets to go, and that's essentially what happens. Is there's a randomization that goes on, and then one computer will start chatting on the network, and then the whole process occurs again. Now, there is a chance in a very large network with a lot of computers that a collision can occur again and occur again. That's where you end up with devices that will help stop collisions, and that's called a switch. And we'll get into what a switch is in a later module. So, CSMA CD is a carrier sense multiple access. It allows multiple computers to get on there, and they can detect collisions. Just to kind of talk about this a little bit more and contrast it, remember I was talking about token ring, where computers pass a token around the network? Well, what token ring wasn't a collision, didn't have collision detection. It was carrier sense multiple access, because there was a carrier that ran around the network, multiple access of computers, but it was collision avoidance. And that collision avoidance mechanism was the token, because only computers that had the token could transmit data on the network. So that was the collision avoidance mechanism. So that was a CSMA CA type network, whereas Ethernet is a CSMA CD type network. So now we get to the section of our module where we're talking about methods of communication, and primarily what we're talking about here is IP communications. So when we're talking about IP communications, we are talking about three different types of, if I can spell communications right, three different types of communications. And what I want to do real quick is I want to draw out a little network diagram here in my truly horrendous handwriting that I have, and but I think it will really give you a better idea of what each of these different types of communication methods that IP uses and how they're different. Okay, so we got computer A, computer B, computer C, and computer D. So a unicast is known as a one-to-one communication. Unicast. Uni meaning one, cast meaning communication or sending. So a unicast, if computer A is going to send some information to computer C, that would be a unicast. They're going to send it directly to computer C. That's a unicast from A to C, one-to-one. Now, we've also talked about in the past broadcast, what a broadcast is. And most people pretty much know what a broadcast is just from using a radio. And what a broadcast is, it's a one-to-all or one to everybody. So if computer A was going to send a broadcast out through the network, well, this broadcast would go to everybody on the network, would flood through all the other ports of this switch except the port that computer A is on. That is a broadcast. Now multicast is a little different. I'm going to change my color ink here just so we can kind of get an idea. Multicast is a little new. It's not really new in the sense of IP communications, but it's more recently starting to be used more and more, and mainly because of this guy right here, because video is really starting to take off, and we're seeing more and more video on our network. So I'm going to add one more computer on this network, and I'm going to call him a server. And this server is not only just a server, but he's going to be a video server. And this could be, you know, any type of, you know, video server. But this video server is going to be sending out, it's going to be broadcasting the World Cup. And the World Cup just a little while ago was really popular, and a lot of people caught that video stream. Now, if you consider the World Cup and the way multicast works, multicast is a one to a group. And what we mean by a group is that not all computers on your network may want to get this video stream, for example. So let's look at this. So say computer A is a guy from, the guy who sits at computer A, he's from Scotland. The guy who sits at computer B, he's from Mexico. The guy who sits at computer D, he's from Brazil. Okay, now all three of these guys love football. And we're talking European football, world football. Americans call it soccer. They love it. And they want to see this video stream. So what they can do is there's a multicast group called World Cup, and they can subscribe to that group, that multicast group, to get the video stream. Now, here's this guy over here in computer C. He's from the US. And this guy, to him, football is the Dallas Cowboys versus the Philadelphia Eagles. It's American football to him. He doesn't want any part of this soccer stuff. So he doesn't care about the World Cup. He doesn't want to get that stream. So instead of flooding his computer with this video stream and tying up his port and using up bandwidth in his part of the network, we can have just these guys here in Scotland, Mexico, and Brazil subscribe to the multicast group for the World Cup, and they all get the data, and we don't flood our entire network with all this large video streaming data that will consume our resources. So the main reason we're going to use a multicast is to reduce our bandwidth, right? Helps conserve bandwidth, especially for large applications. Now, some of you guys may be, some of you folks who are watching this may be IT, like desktop technicians or server guys, And another multicast, another use of multicast is ghost. If you ghost a computer, you're basically taking a copy of or an image of that computer, and then Ghost uses a multicast type mechanism to, especially if you're ghosting like 10 computers at one time. PC manufacturers use this a lot of times, and you'll have one source image that'll be multicast out to a group of computers. So our final segment that we're going to go into is the MAC address. And we've went over the MAC address and how it pertains to the IP address. But one thing we did say is that the MAC address is a unique address. But we never really went into how that MAC address is unique. Well, the MAC address is actually split into two different parts. You have a organizational unique identifier, or an OUI, and then we have a vendor assigned portion. So the difference between these two different portions is the OUI is actually a number that's assigned to manufacturers of network cards. So if we take this MAC address up here, and if we were to look up 002305, we would see that the manufacturer of this NIC card is actually Cisco Systems. So Cisco went to the IEEE, I believe, who manages, honestly, I don't know who hands out OUIs, but he manages, that is a IEEE, manages, they went to the IEEE and requested an OUI, an organizational unique identifier, and so they probably got several of these, but they're using one to make their a round of NICs or a whole bunch of NICs. So you can actually see that there can be a whole lot of manufacturers of network cards, and each manufacturer can make just a tremendous amount of network cards. That's how you can have so many. Now, the MAC address is a 12-character number, but it's a 12 hexadecimal character number. And hexadecimal, well, to back up, the decimal system is what humans use. It's a base 10 numbering system, and we all are pretty well comfortable with it. You count 1 through 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, to 100, to 1,000, to 1 million. They're base 10 numbers, and that's the largest number we have is 10. That's it. It goes up 0 through 9 is it, and then it repeats itself over and over again. Well, there are other numbering systems, and another numbering system is called hexadecimal. And hexadecimal. I'm just not spelling right today at all. So hexadecimal, and hexadecimal is a base 16 numbering system, and how that works, it goes from 0 to F, but there's 16 possible values that you can have. So in each one of these different values, in each of these different slots, you can have a value of 0 through F. So if you think about it, that really gives you a whole, just a tremendous amount more. You can have a whole lot more NIC cards manufactured and use up a smaller value. So here we have just this can go from 0 through 16. In 2 character spots, we can have 256 different values represented in only 2 digits, which is pretty incredible. Well, anyway, I just wanted to kind of go over exactly how a MAC address is broken down. And you can actually, if I do this, I can go to, where did I do this at? I have this pulled up. Here we go. You can go to, if you Google this, you can Google OUI or vendor portion, vendor lookup for MAC address. And what I did a vendor lookup, and I was able to get to coffer.com, And this gives me a way where I can look up, and I actually did this earlier. I looked up 002305, and what we saw is that this is where I found out that this NIC that I actually looked up. I looked it up on my local area network here at my house, and it is a Cisco NIC card. And the chances are this is the NIC. This is probably the NIC card out of my router that I have here on my network. But I just wanted to show you how you can look, if you do this yourself. Open up a command prompt, type ipconfig, look at the MAC address of your home computer, take the first 6 digits and look it up in a vendor lookup page that you can find out on the internet, and you can see who the manufacturer was of your NIC card. It's pretty cool. So there we have it. We have went over a whole lot of stuff today. We went over the Ethernet standards, kind of did a little history of Ethernet, reviewed the protocol that Ethernet uses, which is CSMA CD, and how that functions. We looked at several of the different Ethernet and, let me put this here too, just IP communication methods. I said Ethernet primarily because Ethernet is most commonly used today. And then we broke down further the MAC address and saw how that MAC address, where it lies within the data link layer, and then also how the MAC address is a unique hardware address. It's a lot to go over, and as always, if you have any questions, please feel free to go to the forums. I'm always there. I will answer your questions and help you in any way I can. Again, this is Joe with Router Freak, and I hope you've had a great time this module, and I'll look forward to talking with you next time. Talk to you later. Bye-bye.